Right. Hi, everybody. Thanks for joining this week's installment. So, I want to continue with something from previous lecture, and that is, so I said at the end of last lecture that that if I take GLN, and this would be maybe loops in GLN, and then some, and then this would be either kind of quantum, or maybe Q quantum, or elliptic, or ordinary loops. Then for this, if I take tensor products of evaluation representations, fundamental representations. So that is to say, you take a loop you evaluated at some point, and then you plug in into maybe L, Ki of your defining representation, Cn, and then evaluate at some point AI. This is evaluation where you evaluate the loop. These are realized geometrically as cohomology. And again, this is depending on which cohomology theory you're going to get. This would be different versions of your quantum group of Nakajima varieties. With the quiver which is so not the right kind of. The quiver altogether. This should look like the Dynkin diagram of our Lie algebra. So there's altogether n-1 nodes or vertices, and this is the an -1 quiver. And stable envelopes in all these cases then can be written down more or less reasonably explicitly. And in fact, that's the reason. One reason to think about why is it useful to have explicit formulas for stable envelopes is that we will learn eventually that stable envelopes among many other of the many applications, they in particular give explicit formulas for so-called off-shell. It's not how I spell off-shell. Shell beta eigenfunctions. So eventually we'll talk about some integrable system associated infused with both geometric and representation theoretic meaning, and this are in this particular instance has become some previously studied integrable systems, and then one can in particular find their eigenvalues and eigenfunctions by the following procedure. You write down an ansatz for the eigenfunction, and then this eigenfunction is an actual eigenfunction. It's called the beta ansatz, and then this is and the actual eigenfunction is then this ansatz becomes an actual eigenfunction when the parameters satisfy a certain equation called the beta equation. And there's a certain industry how to write that ansatz in generality, and this is that ansatz is also called the off-shell beta eigenfunction. And so that's this is, again, geometric considerations provide very easy way to do it. So this is interesting. Well, I find it interesting, and I don't want to go into kind of really deep complexity of that, let's just do it. Let's just do GL2 case. It will give you some sort of flavor of what's happening. And then if I take the quiver, my quiver then becomes quiver. Have some spelling problems today. Quiver becomes just a quiver with one node and no arrows. And there's only one evaluation representation. So if you want to compute, if you want to evaluate, well, C2 AI, that corresponds to the cohomology of the space, which we already discussed many times. It's like TG, maybe I goes from 1 to n, and then so this would be TGN, and this is a disjoint union over all k. Well, k goes from 0 to n if you want, of T star Grassmannian of k-dimensional subspace in n-dimensional space. And this is this comes with an action, obvious action of GLN. And inside the GLN, we have diagonal matrices A1 through AN, sit inside here, maybe a torus A. And so the point is that these parameters AI here are these parameters here. Draw a better arrow here. These are the same parameters. And maybe I'll spend some time discussing what stable envelopes look in this particular instance. So this is so let's focus on, since we're interested. So this is let's focus on one Grassmannian, or maybe before we discuss this. So what are the fixed points of my torus? Those are just coordinate subspaces. So it means this is some torus that all matrices diagonal in some basis. And if I look at the coordinate subspaces, there's 2 to the n of them, 2 to the n copies, and they sit inside Grassmannian, sit inside T star of the Grassmannian. And well, we will maybe focus. So if I take up one particular Grassmannian, T star Grassmannian Kn, and this is fixed focus. These are, well, coordinate subspaces. There is a some of them, and there's a, so maybe the cardinality of that state is equal n choose k. So those n choose k coordinate subspaces. And so what would be, how would I think of the corresponding, so it's a classical problem, what the corresponding attracting manifolds look like, and so on and so forth. So attracting manifolds, so maybe let's talk about Grassmannian in some particular parameterization. So maybe we'll think of the Grassmannian. And I apologize for going this in some in maybe too much detail, but sometimes there's a certain classical oh, don't worry about the off shell. I mean, we will talk about that eventually. It's just so this let's talk about Grassmannian in some way or the other. Maybe we want to talk, one way to talk about it, it's the Grassmannian. We parameterize it. maybe I'll just abbreviate it to grass, gr kn. Well, these are n-dimensional subspaces inside n, so this is dimension v equals k, and this v we can parameterize. We can write it as an image, so image of ck mapping to cn, and then we take it. So this means we will write the Grassmannian kn as we take home space of homes from ck to cn. We look at the open set of those of maps which just have rank k, and we mod out by the free action of glk in the source of this map. So this would look concretely, we take matrices of the size n times k, and then of rank full rank, maximal possible rank, modulo column operation. And inside here, the fixed set is the fixed subset fixed points are matrices given. Well, maybe I'll partition it somewhere like that. So I have to choose some coordinate basis. Maybe I can choose it something like maybe one here, one there, and one there. And so this would clearly there's. This is my graph. This is my fixed set. It's a finite set. And then this attracting manifold of that, it's so attracting maybe this is an example of a point, call it maybe P. And then the attracting manifold is the same as the attracting manifold of P. That is the same as the orbit of unipotent matrices applied to that point P. And okay, modulo, this is like, again, like a row operations and like a Gaussian elimination. And the result of the actual attracting manifold looks like this. So modulo GL in action, I can, so this would look so I can make some. So this is modulo GL in action. I can assign this green dots to be arbitrary numbers, no, not dot stars, arbitrary numbers. And so this is, in this case, it's isomorphic. In this particular case, it's isomorphic to, well, in general, it's isomorphic to a copies. This is a special case of a general theorem, Belinsky-Birula theorem. But this in this particular instance, it's coordinate space And I keep writing C, well, it doesn't matter what the ground field is. So in this case, it'll be 8-dimensional. Isomorphic to 8-dimensional coordinate space. This is called Schubert cell. And then we can call maybe sigma p would be the closure of that Schubert cell. This would be a basis in any kind of cohomology theory. And then the classical question in solved long time ago, of which we will see an elliptic generalization today, is that what is the class? Right, and I forgot to say is that there's a very nice parametrization of this data by partitions. Namely, if I take this picture, that I can compress it. I can remove all ones. To be very precise here. So I can compress it down to just that. And then this we can remove. Oop. Didn't want that. I did not want that. So we need 2 here left. Okay. So here if I remove all ones, I get a picture of a partition formed by. So this is, if I read it like this, we get a partition. In this instance would be 4, 2, 2 that fits inside the box of the size k by n minus k. Fits inside the box of n minus k times k. But it's better to think about the complementary partition. So this would be this part. This is the complementary partition, which we denote. Partition lambda, which in this case would be partition 2, 2. It also fits in the same box. I'll just draw it here. The size of this partition, maybe I'll call it lambda c for complementary. The size of this partition lambda c, that is the dimension of sigma p, and the size of partition lambda, that is the codimension of that cycle. And so this would be more important, because this is more important. It's like degree in cohomology, in ordinary cohomology, and that's something. So this would be more. This is a more important thing. And then the standard question is to compute. So if I like the ordinary cohomology of the Grassmannian, this is generated by the Chern classes, by the resolution of diagonal or some other argument, Chern classes of the tautological bundle. Tautological bundle is the bundle. We have a bundle by, well, like for example, the space V, we call it V itself. And so this is another way of saying we have a quotient by GLN, by GLK, and so then so this means the element, the matrix in GNK, those are the churn roots of that bundle. So this is the same as symmetric functions. In S1, maybe call it SK. This is a matrix. This is an element in GL. Sorry, in the group in GLK. Or in fact, in Lie algebra was correct. So if ordinary cohomology, I would lose in the Lie algebra. GLK. This is mod out some ideal, which we maybe don't worry about this too much. And this is analogous to the variable S we had last time when we talked about cohomology of projective space. And so, kind of the old question is that what's the class? Compute the class. What is the class of S? Maybe call it lambda. And the very classical answer to that, this is the Schur function. Since we have so many Schur functions, maybe let me call symmetric functions, let me call churn roots here, let me call them X. X1 through Xk, otherwise it will be Schur function. S lambda of X1 Xk. And this could be written like this. You take a product of xi raised to the power lambda I plus a vector shift that's called rho I. This is the kind of Harish-Chandra shift. And rho is just the vector of 0, 1. Sorry. K minus 1, K minus 2, so forth, 0. And then we divide it by the product of I less than j xi minus xj, and we symmetrize. So this is yeah, we'll prove it in 1 second, but so first, what are these numbers? These numbers here, this lambda I plus rho I, those are the positions of ones. When we think of this, go back here. Sorry, too much. So this is the lambda i's are. So if I take lambda, in this case, has a position of 2, 2, 0, and so this lambda plus rho will have 4, 3, 0, and this differs by 1, and so here the positions are, of ones are positioned by 1, but maybe not so particularly important. This is in the first row, this is in the 4th row, and this is in the 5th row. So the monomials have to do with where these ones occur. And then if I take any kind of expression which is has this sort of van der Monde denominator, that denominator will not be there after symmetrization, because a symmetric expression cannot have, if I have a symmetric expression, then it cannot have a pole of order 1 at the diagonal where you symmetrize two variables. This is actually a polynomial. It's kind of if you've never seen this before, it's very, very important. So this is a polynomial in X. in X. It's kind of very basic thing because if I have, like I said, if I have a symmetric expression that can have a pole of order at least 2 at the diagonal, it cannot have pole of exact order 1. And then by this principle, one can write great many different other symmetric expressions. Namely, you generalize the numerator. You take the numerator. You can replace it. Replace by any generalization of a monomial. Namely, you take some e.g., you can take some function, numbered somehow, take lambda I plus rho I, evaluate xi, and multiply over I. Or this function could be in principle arbitrary function. This could be arbitrary collection of functions. One variable. So if you fix an arbitrary set of functions in one variable and you form this sort of Schur-like expression, then this will be still a polynomial, and you can kind of study a wide variety of that. And you can, for instance, what you can do is you can take, instead of monomial, so we had just like ordinary monomial. So I introduced a new kind of pen, which is a thin black pen, and I keep using what I don't want it. So maybe I'll move it here. So so for instance, this is the case where M, or maybe call it ML of X is just X to the L. This is kind of the simplest kind of monomial. But there are many other interesting functions you can plug in. For instance, this is like ordinary monomial, but instead you can take, for example, like a Newton interpolation monomial instead. So this would be another choice. Or ML of X, you can take X minus A1, X minus A2, and so forth, X minus AL. This has degree L. And so this is like a Newton interpolation. So the corresponding Schur function would be called, maybe I'll put, like star here for or some interpolation. Okay, and this is the class. This is the class of the Schubert cell in equivariant, in A equivariant cohomology of the Grassmannian. It's clear that if you know this, then you know this, because all you need is just you kill the variables A, and if you set all the A's, if you go from here to here, if you set all the AI's to 0, then you go from more covariant cohomology, get to ordinary cohomology, and then from this expression you get to that expression. And that is this is I think was first noted, I believe, so many years ago. Grisha Elshansky and I, we worked on this on various aspects of the theory of the sort of interpolation, Schur function interpolation, other interpolation versions of other symmetric functions like Macdonald polynomials and so forth. And then we were taught by Lascaux and Chausson-Berger that this particular observation they made many years ago. So maybe this should be credited to that. Berger. So this is maybe. So anyway, I've learned that they knew it a long time ago. And what's the proof? So proof is in one line. Well, maybe two lines. Proof that one has correct degree. So equivalent homology is a graded theory. So we have a class of a certain codimension that it has a degree. That's degree size of lambda. It's clear from definition. And then a second, it vanishes at all fixed points. Points that are not in my class here. So this concretely for this function interpolation function has the basic property that if I take as interpolation valid and then evaluated at kind of a mu, which by a mu I mean I stick in as the variable, I stick in the variables. So if I partition mu, I substitute the variables a mu1 plus rho 1, a mu2 plus rho 2, and so forth. So that is 0 unless lambda is a subset in mu. That's very easy to check. So that's it's an elementary thing to check. It's the analog. So this has the property that if I take like this generalizes the property of this function that if I take this function, if I substitute ml into am, that vanishes unless m is greater or equal than l. L m plus something. So maybe m bigger than l. I'm a little bit I'm off by one somewhere, but you can trace this. So there may be a shift by one somewhere, which I'm losing here. So I should have paid closer attention to my notes, but anyway, so that's this two characterized. So there's a unique symmetric function that with this property. So this is a characterization. So this fact. So these two facts. It's a characterization. So if you think of this, there's a unique symmetric function of a certain degree that has this sort of interpolation property, and therefore it has to be the right one. Now, so this is so that okay. Now, more generally, if I take ML, so what was that? What was that ML? So we copy. Maybe I should copy it here. So this is the unique. This is the unique polynomial of degree L that vanishes at some collection of points E1 through L. Unique up to multiple, maybe. Right. Just there's a characterization of also here a characterization up to multiple, but that multiple is also you can also control. Maybe I'll put multiple also controlled up to normal. Multiple you control. And so, but then what does it mean at degree L? So degree L means it has a pole of exact of certain order. At x equals infinity. And maybe if I think of a polynomial as a sections of some line bundle on P1, that would be in that sense. So if I allow polynomials of up to a certain degree, that would be in fact saying that it had infinity as a section of that line bundle. That in fact has a zero. So this is in fact this guy has zero. This guy has zero at sorry, I dropped. This function has zero at has sorry my P1. If I'm thinking of like O of some degree D on P1, so section, so this is my P1, then what I want some sequence of zeros of this guy, and then maybe I want sort of from as a section of that line bundle, I'd like it to have a D minus L fold 0 at infinity. So in that sense, so we previously thought about a monomial. Monomial has like an L fold 0 here and a D minus L fold 0 at infinity in that language. But we might as well take it instead of thinking about like that, we can think of having it differently. So then we have a one collection of points, A1, A2, so forth. And in principle, we can take a completely different collection of points, B1, B2. In principle, one can study functions of this kind. So that would be saying my polynomial ML of x will have the expression x minus A1, x minus A2, B. Maybe I'll start with the D. And then I have some number of factors like this, but also some number of factors like that from the other end. And so then would be L of this and D minus 1 of that. So that's one option. But for particular, since we're interested in not, so this can be studied, but we will have the situation where these are balanced in a way that this BD would be equal to just AD shifted by some. They will be all shifted by one and the same amount, called H bar. And in this instance, you can think of H bar as being some very large number. But in principle, it's small. But in this in this example, you should think of it as large. And so then, this is take that. And so then what we're going to get, then this expression, then the corresponding Schur function that is the so we'll. Sorry, I'm getting a little bit ahead of myself, but the right so one can study this, but with this substitution, with this specialization, one can do kind of more. Namely, one can have a function which is, so maybe I'll write it as whatever, as something. One can study a function which is the symmetrization, and then you can cook in it two different ways. You can either put it like this. You take product of I less than j, and then in addition to the numerator, we're going to put, in addition to denominator, we can put a numerator. Let me just, sign here is slightly important, so maybe you check in my notes for the sign. I think it's plus h bar, and then I take a product of this m l I x I. So this is the sort of expression you see, say, in the world of symmetric functions. This is the kind of expression you see in kind of whole Littlewood type world. Type expression, type function. And then so this, you can study that sort of expression, but you can also study expression of the following kind. So this is, maybe I'll to write an equality. If I divide by the analog of Vandermonde determinant, so this would be shifted, some kind of shifted Vandermonde. So product over all I, either bigger or less than j, hi minus xi plus h bar. So then I'm going to get the symmetrization of this expression. And then I divide I less than j. I take xi minus xj, and here comes xj minus xi plus h bar. So this is, so we'll talk about this in one sec. So this is but well, this is this expression here. That's the stable envelope for a fixed point, for a fixed point in T star of the Grassmannian. That's this. And about this, so again, this would be a special case of what I'll explain in a second. So this has, first of all, that has degree in the variables. If you compute its degree will be k times n minus k, which is 1/2 of the dimension. So this is so stable envelopes for symplectic. We studied for symplectic algebraic variety, they Lagrangian. So they, as degree of symmetric function, they should have a middle dimension, and this is 1/2 of the dimension of Grassmannian. And then they become Schubert cycles, Schubert classes. As lambda when h bar goes to infinity. So when h bar goes to infinity, what is h bar is an invariant parameter that scales. H bar scales this direction. Scales this direction. So if I have an invariant variable and it's then and I send the variable to infinity, then geometrically problem becomes a problem about the fixed locus. So this is a very general geometric principle. So if I have some expression on the manifold, and it depends on the variables. If I send that variable to infinity, then I go to the fixed locus. This becomes, I get something on the fixed locus, and this in my picture here. This means if all these variables, remember this were roughly, if h goes to infinity, all these b's become all these b's here, which are specialized like that. They all go to infinity if h bar goes to infinity. And so my monomials like this becomes ordinary monomials we studied before. And this is the, and what is the comparison between these two functions? These two functions, this difference here. So this says on my T star Grassmannian, this is an open set inside a quotient stack. This is just like we discussed for a projective space last time. And this division here, this expression here makes sense. This is an expression written here. So this says this rational function, which is now this denominator does not cancel as stated. So this is in principle. So this is in principle a rational function. So as stated, it does not cancel out. But it is a regular function. It reduces. So this is some closed subset here, and it becomes a regular function here. Here. So a regular function on the cohomology. So maybe this is like saying, so this inclusion on the cohomology has the property that if I take the cohomology of T star Grassmannian, this is the spec of that is a closed subset. Closed subset in the cohomology of my quotient stack, which is just polynomials. Take polynomials in take the Lie algebra of A plus the Lie algebra plus the Lie algebra of a maximal torus. So maybe Lie algebra of maximal torus in my group G modulo Debye group. So this is where the symmetric. This is where x1 through xk lie, and H is a maximal torus in GLK. So this is where the variables A1 through AN lie. So this is some vector space, and this is a closed subspace here formed by, this is just a union of things that correspond to, in fact, so this is a closed subspace. This is a union of copies of Lie of A corresponding to the fixed point. And the inclusion here is the inclusion by Chern classes of this inclusion here is by Chern roots of the universal bundle, of the tautological bundle. And so right, so this is some closed set, and that expression, which is a rational function a priori, on that closed set becomes a regular expression, and it gives a stable envelope. Or you can take, so in fact, this sits inside. What is this? This is these are the. This is the equivalent weight of the moment map. So this, remind you, this is the T star Grassmannian is obtained as a. So maybe what is T star Grassmannian? T star Grassmannian. You take the set of, take an element in home CK to Cn plus home from Cn, the dual space, to CK, and maybe call this matrices I don't know what to call them. Maybe call them, we already have A, so maybe call them I and J, like Nakajima does. So call this matrix I and call this matrix J. And then the moment map equation is that the composition of them, so that is J composed with I equals 0. This is the moment map. And then we mod out I apologize. We mod out by GLK. So this moment map takes values. So this is, if I think of how my H bar is gonna scale, this moment map, this H bar is scaled by H bar inverse. If this is the part of Grassmannian, these are the cotangent bundles, but scaled by H bar. So this is scaled.
Do you also need some kind of stability?
Right, that's right. So this is home. So maybe I'll take a stable locus and we mod out. Correct. Thank you. The stability is either this is injective or this is surjective. So this means, so there are two choices here. There's either I injective or J surjective. So this scales. So this is the moment map is scaled by H bar, and it takes values in the Lie algebra of GLK. And so instead of talking about classes that live on the, so this expression here which is a good polynomial expression. This is like this is polynomial. So this is a good expression. It's a good cohomology class on the stack, and so this is the same as push forward under the. Since this is the weight of the moment map, this is a polynomial. This is a push forward from mu inverse 0 to the whole stack. between between this and this is right. So maybe I introduce so this is open in mu inverse 0. So this was what I wrote. Sorry, I apologize. What I wrote is incorrect. This is open in here, so stable locus in here, and this is closed in the in just some kind of vector space stack, which is what I wrote here. So this is vector space, some stack of this home plus home over GLK, right? So this object is the cohomology of that quotient stack, and this is and the difference between being a class here and being a class there, you can account for that difference by this factor here. Well, strictly speaking, I should have, maybe I apologize. I should have, very strictly speaking, I should have put it over all or I and j, and then here I would have an extra h bar to the power k. So that would be actually correct. So now finally elliptic analog of that. Elliptic version is sort of the obvious one, is to replace, take what we were doing, take elliptic envelopes for t star pn minus 1 as our functions. Because this is all this expression we were writing, the expressions we write, they have the property that if k is equal 1, so if k is equal 1, then t star Grassmannian kn becomes this. Right? So the previous everything we write in the case when we don't have denominators, when we don't have to symmetrize, we just get t star pn, and then this is we already know what the envelopes are there, and so that should be this. And then so this is a product, and you remember this the elliptic envelopes for t star pn, they already had exactly this. I mean, they had this exact feature, so they had maybe slightly different. So FML had that feature of x. Well, we wrote it for s, and with this s, you should think of x inverse maybe that had the features that this was theta of a1 times s, so forth. Then at some point we had something interesting. We had a l s z h bar like n minus l divided by theta of z h bar n minus l, and then it's continued to theta a n h bar s. Okay, so if we transform, so this is the analog. This object is the analog of ai minus x. If I write it additively, since x is inverse, so this is, and this is the new piece where the dynamical variable come in. New piece with dynamical variable. And then we divide. So actually, so maybe has the same expression is symmetrized. This sort of the same kind of product of ML xi, and then I take theta of theta I less than j, theta xi over xj, and then theta of I think that is correct. I mean, sorry, this is the so that is the expression. So this is again, this is regular. It's actual elliptic, so this is actual element. Actual elliptic class. Class, if we push it forward to the stack, to this home plus home, more GLK stack, then this will multiply. This would give us expression sim. This sort of expression. Sorry, I should have developed some kind of shorthand here. And so this is and how these expressions are proven. So there's a general proof follows a general idea of Daniel Schenfeld. And then it says that if I take the moment map, so this would be all the very schematic, since I've already spent most of the lecture talking about this particular instance. So this you take mu inverse of a non-abelian group G. So this is G is GLN. So we have G GLN, GLK, sorry. And inside here there's a maximal torus. H is isomorphic to torus. So H maximal torus. So if I take mu inverse of 0 and mod it, well, let me mod it like that. So mod it by G. There is so this would be a caricature, but the caricature is the following: that there is a correspondence between things like this. If I change the group in symplectic Hamiltonian reduction, I get things like, so this is should be taken with a grain of salt. You have to look at, maybe Schenfeld wrote a PhD thesis which is available online. If you search mass sign you can find it. So this is what you can do is you can first take same equations, divide out by a smaller group, and then you can this embeds into take this. There's a diagram of this side. And what about this diagram? So this diagram is, for all intents and purposes, is essentially a smooth Lagrangian correspondence. So this is the since the beauty of the moment map is that the things which are, you know, the moment map directions are sit in the dual of the Lie algebra, so exactly dual to the group directions, and so this is the inclusion here is exactly, these directions are exactly dual to directions that are without quotient. So this kind of makes sense. I mean, the fact that it's smooth, it's also, you can, I mean, smooth in a certain sense. And that object here, this object here, this is a hypertoric variety. It's when we act for, if G was acting on if G for actions, for original space, if G was acting on a vector space, such as home plus home. So these are home plus home. Right. So this is a vector space, and it's a reduction of a vector space by so you take a moment map for a torus and you divide by a torus. So it's a hypertoric variety, and for this we know elliptic envelopes explicitly. And now elliptic envelopes are explicit in the sense that elliptic envelopes are sections of some bundle. So if you're applying a general procedure such as pullback and push forward, you know which bundle they're gonna go. So this would give if elliptic envelopes are characterized as a certain section of some line bundle, and being a section of some line bundle is preserved by things like pullback and push forward. So I mean, if you do it correctly, and so this operation does give you things like that. And so this is, you can think of what is this what's the inversion of push forward and what's the pull. So this is, so to go from here to here, we need to invert push forward, and we need to invert. There's a push forward here. So this, we have to invert the push forward here, and so that would be saying what? So the invert this involves inverting this involves things like 1 over theta xi minus xj bar, this sort of thing, because these are the weights of the moment map, the off diagonal weights of the moment map. Off. And pushing this forward involves things, because this is actual integration. This push forward involves things like, because these are the tangent weights. So these are the tangent weights to G mod H. These are roots. And now So you can ask why only product over I less than J? So this is, you can ask why if I'm saying what I'm saying is correct, why don't I get in this formulas like this, why do I get products over only half of this? And of course, the reason being is that you have to trace, we have to really trace, have to really look at the, you know, have to really separate into to look into actual geometry. E.g., if I take G mod H, so if this is a complex group, so GLN, I take GLK, sorry, GLK mod mod H. Well, what does it look like? This is like a general. This is like a general conjugacy class. So as a manifold, I would be isomorphic to T star of the flag manifold of GLN. And so this is, you can't really integrate over that. So you can't, this is something non-compact, and you can only integrate over this part. So this is we look at some class, you know, the way this is set up, there's a class which actual integration only happens through over this. And similar with the moment map, it's only half of the variables in, you know, you do it correctly, it's always half of the variables you integrate. So you only integrate. But this is not something I'm going to explain, but absolutely general, very general. And speak in the EG for, so this is a very general thing to write. So if you're interested in formulas for elliptic stable envelopes, this is EG for maybe for the Hilbert scheme of points, maybe my favorite example. K, C2K. Can find formulas in Smirnov. So Schoenfeld, in Schoenfeld's thesis, he gives, so if you want actual formulas for like partial flag manifolds and other Akajima varieties of type A, in this be good. You can look at the in Schoenfeld's thesis, but if you want to look beyond that, you take the Hilbert scheme of points. This is Andrei Smirnov wrote down formulas. They're quite a bit more complicated this, but the general principle is the same. It's a hypertoric expression, which is in the end symmetrized. So that's okay. So this is, I apologize, took us a long time. But it's questions about this part. I've only have 15 minutes left for what I was actually going to talk about, but
Can you say something about the appearance of P1 and these sections of O of D on P1 and the formulas for ML and cohomology?
well, in this case, so what is this for Grassmannian? So for Grassmannian, not P1, Pn, right? For T star, if I want here T star Grassmannian, Kn, then this correspondence would be between, you take just k copies of T star Pn minus 1 k copies. That's the correspondence. So this is the fact that we get elliptic stable element for projective space. We looked at them explicitly last time, and this is where that functions ML live. But the fact that this somehow, the fact that you should think of them as sections of something, this is well, pretty clear, because this it really is an interpolation problem when you think about it. You think of this, if the cohomology, or whatever, elliptic cohomology, elliptic cohomology of T star Tn minus 1, that's this sits inside my, so there was the stack S, and there were these variables A and maybe also H bar, and then there's some kind of things like that. So where this is where S was equal to AI inverse, but also there is a flop where we had the S equals AI inverse H bar inverse, something like that. And so this is the things we want to write are the polynomials in S that have a certain behavior at this point, right? I mean, the elliptic stable envelope is something which is, so elliptic stable envelope is first of all flop. This is my, maybe I should write. This is the elliptic stable envelope of Pn minus 1. Sorry, the elliptic homology of that, and this is for the flop. And so elliptic stable envelope there, it has to be, so elliptic stable envelopes here are on the stack. So general principles, in particular true here, are flop invariant. And vanish outside of the attracting manifold, of the full attracting set. So this means there's sections of a line bundle of degree n in S, right? So we decided degree of a line bundle is given by a quadratic form. So that quadratic form, i.e., degree in S is a quadratic form. Degree in S equals n times S squared. So that would be more appropriate. And then the vanish precisely at the points where we would like them to vanish, where vanish at precisely at the complementary points. So if we now draw kind of a S line here. Sorry, I meant something else. If we fix it for some given value of S, they will have to vanish. So if I have some fixed point, they will have to vanish, something like that. So the order of fixed points is exactly flopped under the flop, right? So this ordering here. So is reversed. this is easy to understand. Why is the order exactly reversed? Is that because if I have a fixed point, one point P1 and another point P2, then I have an attracting line between them. There are two things need to happen. I have to have an effective curve. So this means I have to have an effect. So if I have maybe an ample bundle, suppose I have, that's actually kind of useful lemma anyway. So suppose I have O of 1 is an ample bundle. So if I have my attracting curve and it has some weight, which is maybe has the weight W, which is attractive weight, tangent weight, then if I want to compute the degree of my curve with respect to, maybe I'll pair my curve, maybe important to pair my curve C with O of 1. Well, what's it going to be? By localization, I have to take the weight of O of 1, O of 1 at P1 minus the weight of O of 1 P2 and divide by W. This is positive. This is decided that this is positive. And this is being an ample bundle, it's also positive. And so it has to be the case that this is therefore positive, right? And so now if I have a flop, then the weight of the what was ample before becomes anti-ample now. And so this ordering is exactly reversed. So we have a flop, and the attracting what was attracting before is repelling now. And so this is this says that if I had this picture, so maybe remember we had this picture. So maybe I'll just finish. Maybe I'll skip talking about things like what was actually indicated by this by the diagram in the background. So maybe we're not going to talk about that today. Remember last time we had this picture, so we know something like that. We had maybe this fixed point in attracting directions go like that. And so then the stable envelope means it was non-zero at this point and this point, but vanished here. Here vanished. Now, what will happen under a flop is that at this line will now go up like that, right? And so here I had my right. And so now maybe I should have labeled this line somehow. Maybe one and two is the 1 and 2 are the lines where I actually my fixed points, and just actually 1 and 2, it's my fixed point. And then there's line 3. And so now this is 1, this is 2, and this is 3. And 1 and 2 is my fixed point here. This is it. And then this is attracting manifold. Looks like that now. It now the 2 and 3 it hits, but at this point vanishes. So where it was vanishing before the flop is exactly complementary to where it was vanishing after, except for my my fixed point. It's always never vanishing at a given fixed point, but that otherwise it's exactly opposite. And so you get exactly the case that you have a section of a certain bundle, and it vanishes. It vanishes precisely at some number of points from the beginning, some number of points from the end, and then there's one interesting term which is, where was that? So this is this new piece. You get this one new term. More questions? So the plan is then we'll move the Young-Baxter discussion to next time. So I'm not going to start it today. Maybe.
So maybe you've answered the question I tried to ask, and if so, I apologize. But so way back in the beginning of the talk, when you were picking the M's that led to the Schubert classes, or yeah. So those M's, they arose as sections of bundles on Pn-1, or sections on
P1.
P1. Yeah. So
P1.
my question, I guess, was where does that P1 come from? Or
P1
how to
is
understand
the
that P1.
generation, right? So okay, so maybe I'll explain this one more time. So this is so we have so elliptic homology. So is defined. So in principle, for an elliptic curve, so you have a elliptic curve. Maybe we'll write it something like irreducible genus 1 and a point plus a point, which is here. Just here, this point at infinity. Right? But also, but also, it doesn't have to be smooth. It's with a plus a smooth point. But you can also can be nodal. So it is isomorphic to P1 with 2 points identified. It's going to have 0 equal to infinity if you want. So maybe 2 points identified. 2 points identified, or it can be cuspidal. And so this is the elliptic stable levels. They defined over this, whatever whole variety of elliptic curves defined for anything. And so this becomes a covariant K theory. And this becomes a covariant homology. And so this is what was when we were talking about sections. So a variable S here S was sitting on an elliptic curve, and stable envelope for P1 for T star Pn. So this elliptic curve, which is this elliptic curve here was the Chern class. This is where the Chern root of the tautological bundle of 1, I'll just write. And so this has stable envelope for T star Pn-1. This was a section of a line bundle on this elliptic curve of degree we decided will be equals n. So this is and it was vanishing at the points roughly like a1, a2, a whatever k minus 1, and then a n h bar a n minus 1 h bar, this sort of thing, right? That makes sense because those are the this is where the fixed points are. Those are the fixed points. That make clear. So this is elliptic homology of T star Pn. This was this sits in the product of all these variables, and this really is that's where that S variable hits the. So this is kind of this is. I don't know what's the appropriate color here. Maybe I'll try the. This is this base direction where my A's and H bar lives, and this is where the S variable lives, and this is cohomology of the variety, and this is cohomology of the flop. And now, upon degeneration to here, I get this E becomes C star, really. Kind of the smooth locus and this. So this contains C star, the smooth locus. So E is really that C star. And this is the churn root for O of 1 in now covariant K theory. K covariant of T star Pn minus 1. And it's characterized exactly the same way. And then further becomes, if we trace it here, so it then becomes kind of C, where that C is really again this is the smooth part. So this cuspidal curve contains that C, and that's with, well, maybe I should the dual rather. Sorry, there's some up to duality, so it's more like peak of that. See, now maybe C now sits in the C is more like in the peak of C is in fact peak 0. The cuspidal curve. And then again, it's the churn root. It is the variable S is again churn root of O1. So, and it again has the property that it has to vanish at all this, at some number of points at the beginning, some number of points at the end. And it has a certain degree, but just because it came by degeneration by degree of some line bundle on here. In fact, degree, whatever degree. Well, there I said D, but it's like N. Is that helpful?
Very, very, yeah.
So while you can ask, so kind of fundamental property is that all this somehow everything we do is flat in the elliptic curve. So that is to say, this is like, for example, the elliptic, well, very fancy groups, like, for example, this is the very fancy groups we consider Well, in fact, the flat deformation once you don't. This depends on parameters, and this says that many things you can compute an ordinary cohomology or K theory, and so this requires that well, the fact that stable envelopes are flat and this, well, that's actually kind of it's corollary of the construction, because if you chase the construction was in terms of some cohomology vanishing, and that cohomology vanishing continues to hold if you formulate it suitably, that continues to hold um, in this through that degeneration. And I have to work a little bit, but this can be shown. And so then so there's many computations in this business. One doesn't need to do the full elliptic. I mean, in fact, I advise people not to start with the full elliptic computation, because full elliptic computation is usually very complicated, and it may be very often it may be best to describe that a certain unique elliptic deformation of something where you compute an ordinary cohomology, or in ordinary K theory. So that is actually, I think, very productive way of looking at it. It's you don't wake up in the morning and try to work with elliptic quantum group. You first warm up with more familiar rational or trigonometric expression, and then if need be, you can if you formulate everything correctly geometrically, then this would all go through with into an elliptic situation. More questions? Well, maybe I have rather than a question, I have maybe I understand everybody's tired and that this course is going a lot slower than I was planning to go, but at the moment I appreciate everybody who's tuning in and at the moment my plan is to continue to go at more or less the same pace. So because I kind of want to get somewhere, and when requires, fortunately, many steps require explanation, and so I unless there's a strong desire to somehow wrap things up as fast as we could and get to some conclusions without details, that could be done. But and you can, if there is a sentiment to that effect, then maybe we should have a discussion in the course Telegram channel. But my own feeling is that I would like to continue at the same pace without speeding up, because things take a certain time to explain. So we don't have to decide this now, but if you feel like it's been going long enough without getting to the results you want to hear, then we can jump to the conclusions. But I would my personal inclination is not to do that. So well, to be continued. Thanks everybody for devoting your attention to this complicated subject in the middle of the summer, and I'll see everybody next time.